All right, so welcome to Friday, October 16th. Start a new unit today. Our next test isn't until November 4th or 5th, so it's a ways away. As I was saying before I started recording, the lesson today is a little bit longer than normal. A lot of stuff involved, and for that reason, if we don't make it through, we have Monday to catch up. I think we'll make it through everything, and then Monday will just be me working some of these problems. So Monday will be a lighter day, but the trade-off is today is maybe a heavier day than normal. So having said that, let's jump in and talk about Extrema. Extremes, but we like to sound fancy, so we use the word Extrema. See if we can get the camera to focus and lock focus so it doesn't zoom in and out all the time. Extrema on an interval. So the maximums and the minimums on a given range of graph or data or whatever. So first, the extreme value theorem. This is one that I think once we explain it, it'll make sense. It's not like a formula you got to memorize. It's just an explanation of things that, well, let's just do it. I think it'll make sense to you. If f is continuous, on AB, and that's AB with brackets, meaning it has to be a closed interval. We'll see why in a minute. So if AB is continuous on a closed interval, then F has both a minimum and a maximum. We'll draw some pictures and see how this makes sense. If f is continuous on the closed interval, so you got to include the endpoints, then f has a minimum and a maximum. So let's graph something from A to B. And I want your graph to look at least somewhat like my graph for this particular problem. So let's go up a little bit, come down even more, and go up a whole lot more. Something like that. Right, that graph has an absolute max, meaning as opposed to a relative max. Well, the relative max we'll talk about in a minute. Has an absolute max at x equals. So which value of x is our graph the highest at? B. Good. At x equals b. By the way, that happens to be an endpoint. That becomes really important later. If I remember, I'll try to circle back to that. It's not always an endpoint, but it might be an endpoint. Another word for the absolute is global. So like overall max, absolute max, global max on that interval is at x equals b. It has an absolute min, or global min, minimum, at, where's the minimum at? D, at x equals D. And it has a relative max, or a local maximum. Local might be even a better term. So local, like in its neighborhood, has a local max at x equals C. Right, C is the top of a hill. So in his little neighborhood, and you can define the neighborhood as narrow as you want to define it, in C's neighborhood, he's at the top of the hill, so he's a local max. He's a relative maximum. It's not the overall maximum, not the absolute or global max, but he's a relative max. All right, let's look at a couple things that would mess up this theorem. So if it's continuous, so let's look at one that's not continuous and see why that would mess this up. So again, we'll go A to B. So not continuous. That would be like maybe something with an asymptote. Well, it has an absolute min at least. Oh, I should have drawn that a little bit lower to make the absolute min at x equals b. But there is no absolute max. Right, it just goes up forever. There's not a number. You can say it goes to infinity, but that's not an answer for, what's the maximum? Well, there's not a maximum. It just goes up forever. Second sort of possible problem, jumping around here, is the open interval, closed interval thing. So let's do one that has an open interval, meaning at the endpoints we don't want to include the endpoints. So I want open circles at the endpoints. So that one does have an absolute minimum. At x equals c. This is what throws people off, is that there is no absolute max. Okay, the reason is at x equals b, there's not a point there. So, yeah, whatever this y value is over here, just say it's 17. So no values go above 17, but no values get to 17. So there's no max. And you can say, well, it's almost 17. Yeah, but the absolute max isn't 16.9 because it's more than that. It's not 16.99 because it's more than that. It's not 16.99999 because it's more than that. But it's not 17. So there's no way to describe an absolute max. Even though there's like a cap on the whole graph, there's no number that describes its maximum. Does that make sense? That's probably the confusingest, the most confusing part of this part of the lesson anyway, is that, well, it looks like nothing is above that, but there's still no number that describes that y value. Yes, sir.
So if the graph was the other way, could there be a maximum, but not a minimum?
Sure. Yeah, then so the extreme value theorem says if it's continuous on a closed interval, you're guaranteed to have a minimum and a maximum. It's possible that you, even if it's not closed, to have a maximum and a minimum. If you did something like that, that would have a maximum and a minimum, but not because of the extreme value theorem, just because you happen to get lucky and get a graph that did.
Oh, yeah.
So good question. I think you were specifically asking if it was.
Basically, like inverse.
So if it was the bottom one.
Yeah.
Oops. There we go. That one has a max, but no min. This one has a max and a min, but not because of the extreme value theorem, just because we got lucky. All right, so if you got an equation that's continuous on a closed interval, then there will be a maximum or minimum. It might be at an endpoint, though. All right, then we're gonna define a different thing and then put those two ideas together. Definition of a critical number. I mean, critical makes it sound important, and it is. So the definition of a critical number. Right. Let f of x be defined at x equals c. So that means that the function has to exist there. If f prime of c equals 0, or f prime of c is undefined, then c is a critical number. If the derivative is 0, or if the derivative is undefined, then there's a critical number there. Here's a little bit of why. If f prime is 0, then you've got a horizontal tangent line. If f prime is undefined, then you either have a vertical tangent line or you could have a cusp. So a critical number is something weird, something unusual, or something important is going on with the function, because you either got a horizontal tangent line, a vertical tangent line, or a cusp. So these points are important, and this is why we've set the derivative equal to 0 before, and why we've asked where is it undefined before, because we're going to use those, because those make critical numbers, because critical numbers, something different, strange, important, is going on the graph if we have a critical number. All right, now we're going to put the idea of extreme values and critical numbers together. All relative extrema so not absolute or global, but relative, so top of mountain, bottom of valley, all relative extrema occur only at critical numbers. Phrase it a different way. Going backwards, though, not all critical numbers make extrema, but all extrema come from the pool of critical numbers. Venn diagram for the visually inclined. So you got this big pool of critical numbers from setting the derivative equal to 0 or figuring out where it's undefined. So you got 4 or 5 options that are critical numbers. Within that set of critical numbers, you have all of the relative extrema. So maxes and mins are relative extrema and critical numbers. But you could have critical numbers that aren't relative extrema. Like if you have a horizontal tangent line that just keeps on increasing like that, that's a critical number but not an extrema. The vertical tangent line is a critical number but not an extrema. I guess the cusp we could put in the relative extrema group. That's a critical number and a relative extrema. Now, the reason we have to kind of go through this is that we have a process for finding critical numbers. Find using f prime. The relative extrema, there's not really a process other than test the critical numbers. Or check the critical numbers. So the mathematical process gives us the critical numbers, but those aren't exactly the answers. We take that pool of possible answers and then check them to see which ones are relative extrema. So it would be nice if you could just jump straight to relative extrema, because that's what a lot of this week is about, next week, maxes and mins. But you can't really jump straight there. You start with critical numbers and then you check to see, well, are they relative extrema or not? So we'll kind of go through that process. We'll do some examples where we find critical numbers, just find critical numbers, and then we'll jump over and see if we can find the extrema based on our critical numbers. All right, so this is sort of part one of the process, is find critical numbers. Find the critical numbers 4. We'll do some examples of finding critical numbers. So these are potential extrema, but not necessarily extrema. We'll worry about that later. So critical numbers, that's f prime is 0 or f prime is undefined. So f of x equals x squared minus 7x plus 12. Critical numbers, where the derivative is 0 or undefined. So let's find the derivative. 2x minus 7. And I want to know where that's 0 or undefined. So for 0, we'll set it equal to 0. And we get x equals 7 halves. And it's not undefined anywhere. It's defined everywhere. So I don't have to worry about an undefined part for that derivative. It's never undefined. It's always defined. So x equals 7 halves is a critical number. By the way, what shape is this thing? X squared. What if I graph that? What's it going to look like? Parabola. I'm guessing x equals 7 halves is where the vertex is. So that, in fact, that the old vertex formula, negative b over 2a, that comes from calculus. Like, we don't tell you that in algebra. We just say, here, use negative b over 2a. but it comes from this critical number, minimum, maximum stuff in calculus. Number 2, f of x equals x over x plus 3. Well, I need to find that derivative. Quotient rule. So why don't you take a second to use the quotient rule and find that derivative. So make f be the top, g be the bottom. F prime and g prime are easy. Then gf prime minus fg prime all over g squared. The x's cancel, and 3 over x plus 3 squared. And so we want to know where it's 0. Well, it's never 0. F prime is never 0. Because there's nothing to make this, or we could kind of look at it like this. The only thing that makes a fraction 0 is if the top is 0. So I'm never going to have a 0 for an answer there. There's no x value that will make that work. But it is undefined at x equals, what value of x makes that blow up? What makes it not work? -3. So that means that -3 is a critical number. So in those first two examples, we had a critical number where f prime was 0, and a critical number where f prime was undefined. And you could have both. Speaking of, let's do this example. F of x equals 2x minus 3x to the 2/3. So f prime of x equals 2, I guess at least that one's easy, minus 3 times 2/3 times x to the -1/3. So that would be 2 minus, I'm going to rewrite that as 2 over x to the 1/3 because I don't like negative exponents. And then if I really want to check where that's 0, I'll need to get a common denominator. That was a key step on one of the test questions yesterday, one of those e to the x ones. If you remember that, you took a derivative, but your derivative didn't match your answer choices because you needed to get a common denominator. If you had, well, you could have avoided that, but if you avoided it, you would have had an ugly quotient rule. So hopefully you used algebra to split up the natural log, take the derivatives individually, and then put them back together with a common denominator. Getting some blank stares, so you don't know which one I'm talking about. Or you do know which one I'm talking about, and you're frustrated now because you didn't get it. All right, so common denominator, x to the 1/3. So where this thing is 0 would be f prime equals 0 if the top is equal to 0. So let's move things around. So that means 2 equals 2x to the 1/3. That means x to the 1/3 equals 1. If I cube both sides, I get x equals 1. F prime is undefined when the bottom equals 0 because we can't divide by 0. So that would just be if x equals 0. So two critical numbers, one from derivative equals 0, one from derivative undefined. So you always got to look for both, is what that example, what all of these examples are trying to show. Set it equal to 0, but also think about if it's undefined. We're doing fine on time. We're 2/3 of the way through or so. All right, this one's more about trig, but we're still trying to find critical numbers for f of x equals 2 sine x minus cosine 2x on 0 to 2 pi. I think you know this by now, but the reason we throw the limited domain on there is because it limits the number of answers. Right? Otherwise, you're left spinning around the unit circle forever. You know, you get 2 answers, then you add 2 pi and 4 pi and 6 pi and 8 pi. And so a lot of times they put this on the end of it so that you don't have to worry about all the extra answers. Just get the main ones and then you're good. Alright, so f prime of x would be, let's see, derivative of sine would be cosine. That's an easy one. Derivative of cosine would be negative sine of 2x times 2 by the chain rule. Some of you earned yourself a Tootsie Roll Pop based on that test yesterday. Not in a good way. You missed some chain rules. So let's set that equal to 0 to figure out where our critical numbers are. There's nowhere where it's undefined, so I don't have to worry about that. And honestly, that happens most of the time. You usually don't have to worry about undefined. The trouble is, when you do have to worry about it, you've stopped worrying about it and you forget about it. So you always got to be thinking 0 or undefined. And a lot of times you can throw out the undefined, but you got to think about it first. This looks terrible. And I think the only reason I did this one is because you might need this in the assignment today. But sine of 2x, I don't expect you to remember this trig identity, which is why I'm doing this problem right now. But sine of 2x equals 2 sine x cosine x. I don't remember that. I don't expect you to remember that. That's why I'm giving it to you now. You don't really need to know trig identities in here other than a tangent equals sine over cosine, and sine squared plus cosine squared is 1. Like, beyond that, you don't need to know this kind of stuff. And so I wish the book wouldn't throw it in there, but it did. Speaking of tests yesterday, I can factor out a 2 cosine x, and that would leave 1 plus 2 sine of x. And now is why where we learn why the book and CalcChat and multiple choice test and me keep doing algebra stuff like this. Like, why are you doing that? Why don't you just leave this as your answer or leave this as your answer? Well, it's because now we want to set this equal to 0, and it's a whole lot easier to set factors equal to 0. So that's why that's why we keep factoring things out, because when you have factors, you can set each factor equal to 0. can't do that with things that are added, but you can do it with things that are multiplied. So let's see, cosine of x equals 0. That happens at, see, cosine is the left-right thing, so that would be right there and right there. So pi over 2 and 3 pi over 2. Still built-in trig review here. Sine of x equals negative 1/2. So negative sine is the y-coordinate, the up and down coordinate, so that's the down stuff. 1/2 is the shorter side. So that would be 7 pi over 6 and 11 pi over 6. So that example was more about trig than anything. Those are our critical numbers because the derivative was equal to 0. And anytime the derivative is 0, any critical numbers you have are potential extrema. So we worked on some examples of finding the critical numbers. The last step, and we'll do one example of this, is to use our potential extrema, use our pool of critical numbers, and figure out which ones of them are extrema. So, like, how do we narrow down from we know how to get the critical numbers, that's the big circle, but then how do we figure out which one of our big circle numbers fit into the relative extrema category? And so that's the last example. Find the extrema we'll say the absolute extrema. If it doesn't say absolute or relative, it means absolute. It needs to say relative if it means relative. So find the absolute extrema of f of x equals 3x to the fourth minus 4x cubed on negative 2 to 2. All right, so our thought process is before we find extrema, we'll find critical points, and then we'll test them to see if they are the extrema or not. So first, critical points would be where the derivative is equal to 0. 12x cubed minus 12x squared. Set that equal to 0. What started out looking like a terrible problem simplified pretty quick. We factor out a 12x squared. So x equals 0 and x equals 1. Critical points. And critical points meaning they are maybe extrema, maybe not. Possible extrema. So we'll test with a table of values with critical points and endpoints. If I had a nickel for every time I saw a table of values that did not include the endpoints, I could at least go buy myself lunch today. So critical numbers, or Extrema could be endpoints. That was the very first thing we saw, rewinding all the way back to the first picture we drew. That absolute max occurred at an endpoint, so we need to check that. The min didn't, but it occurred at a critical number. So when we make our table of values, we've got to include the endpoints. So my endpoints for this one were -2 and 2. And I don't guess you have to put them on in order, but it sure makes sense to me to put them on in order. So the endpoints are -2 and 2. The two critical numbers we got were 0 and 1. So two critical numbers, two endpoints for this one. I guess you'll always have two endpoints. You could have any number of critical numbers. And we want to test them into the original and just compare their y values. We don't want to graph the whole thing. We just want to check these key points, endpoints, and critical numbers to see who's the highest and who's the lowest. So f of -2. Again, I'm going back to my original function. Well, that's kind of a pain, but let's see, 2 to the 4th would be 16. Yep, times 3 is 48. Minus 4 times -8. Let's see, 48 and 32 make 80. Seems like a good candidate for a maximum, but let's find all of them and see what happens. F of 0, that's an easy one. 0 to the 4th minus 40 cubed. 0. This is the easy part of the problem, just plugging in numbers. F of 1, 3 times 1 to the 4th minus 4 times 1 cubed. It's -1. And f of 2. 3, 2 to the 4th minus 4, 2 cubed. Yep. So 3 times 16 is 48. Minus 8 times 4 is 32. 16. Okay, so now I'm ready to answer the question. All I'm going to do is look at my y values and say there's an absolute max at -280, because that has the biggest y value. So there's an absolute max at -280. And there's an absolute min at, let's see, the smallest y value is 1, -1. And then, just to be clear, because sometimes it asks crazy questions, the x value is where it happens, or where the max is. The y value is what the max is. So you got to read the question carefully sometimes. Although, if you'll always answer with the point, you'll cover it. So if they say, well, where is it? You could get by with just saying x equals -2 or x equals 1. If they say, what is it? You have to give the y value. But the safest thing to do is to just give the point. That way you got yourself covered. All right, the assignments from the book, page 167, 1 through 45, but not all 45. Every other odd, EOO, every other odd. So that's divided by 4, so that's 12 problems, I think. But there's a lot going on, so read the questions carefully, give them a try. Do some of them before Monday. Again, Monday, no new notes. I will just do some of those problems. But it goes much better if you've tried them and you've got questions on them. Of course, course, if you do them all, then you won't have anything to worry about next Monday. All right, so longer than normal notes, but the trade-off is you get a no notes day on Monday. Well, not no notes, no new notes anyway. We'll just work some example problems.